Okay, let's take a look at section 7.5, solving trigonometric equations. One of the key things that's listed in this section is in the third paragraph on page 456. Talks about principal values. Principal values are basically the first time that we're going to look at either positive or negative cases. We want to keep it in two consecutive quadrants. So let's start with the x values. That would be cosine of some theta. And for cosine of theta, principal values are in the first and second quadrants. Now, why is that? Well, cosine theta is the x value, all right? And in the first quadrant, x is always positive. In the second quadrant, x is always negative. So you have two together, two quadrants, and you have both positive and negative values taken care of. So for cosine, this would be the principal values in the first and second. Let's move on to sine. If we use sine in both the first and second, well, that's positive everywhere. That's the y value. So we can't use that. We don't want to use the second and third. So what is used is the first and fourth. Again, in the first quadrant, sine is positive like everything is. But in the fourth, instead of going counterclockwise, if you go clockwise from there, you have both positive and negative values for y, and that's what's used. Well, also, tangent of theta uses the same two. For some reason, instead of going first and second, they went first and fourth. So if you can remember sine has the same, with its two in the first and the fourth, you're going from negative pi over 2 to pi over 2, or negative 90 to 90. Whereas for cosine, in the first and second, you're going from 0 to 180, or 0 to pi. Let's take a look at an example that has problems like this. Example 1. It says solve sine of x cosine of x minus 1/2 cosine of x is equal to 0, and it says specifically for principal values of x. Now, if it doesn't say principal values of x, then it's either got to limit it, or you've got to give all the values, which could occur with the that particular value plus 2 pi n or pi n, something like that we've done before. Well, let's take a look at this. The very first thing, this is different than the previous three sections. It's an equation. So we've got to solve for something. Well, both of these two terms have a common factor of cosine of x. So I'm going to bring that out, have cosine of x times what's left over. For the first term, sine of x minus 1/2. And that's equal to 0. Well, now we have two factors. The cosine of x on the outside, the sine of x minus 1/2 on the inside. So I'm going to set both of them equal to 0. Cosine of x equal to 0. Sine of x minus 1/2 equal to 0. Well, let's start with the cosine. Where in the first two quadrants, because it asked principal values here, is cosine equal to 0? Well, looking at the clock, all the way, x is equal to 90 degrees, or if you were in radians, pi over 2 radians. That's the only place in the first two quadrants where cosine is equal to 0. So x is 90 degrees there. Well, for the second factor, the sine of x minus 1/2, let's take the 1/2 and move it to the other side. And so we have sine of x is equal to positive 1/2. Now for sine, its principal values occur in the first and fourth quadrants. So we're 90 degrees forward, we're 90 degrees negative forward and back from 0? Well, it's positive. So number one, we're going to be in the first quadrant. But where is sine of some angle equal to 1/2? This goes back to our special values. It's either 30, 45, or 60. And in this case, x is equal to 30 degrees. So for one factor, the first factor here, we have cosine of x is equal to 0, x is 90. For our second factor, we come up with an equation, sine of x equals 1/2, x has got to equal 30. Those are our two solutions for this particular equation in for principal values, right? That's it. Now then, let's take a look at example 2. For this one, it says solve cosine squared of x minus cosine of x plus 1 is equal to sine squared x. Now they limit what x can be. It's no longer principal values for this one. It says when x is between 2 pi, notice that the or equal to is not included, but on the lower end it is, and that's from 0. Okay? So it's the first time around our circle, but we don't include the stopping point 2 pi, because that would be in the same position as 0 would have been. All right? But you just have to watch, because sometimes they will include it. The very first thing that we don't like about this is, well, it's got cosines and sines in the same problem. If you think of this as variables, we can only solve an equation if it has one variable. We've got two variables here. We've got cosine of x and we've got sine of x. They're different. So let's take, since we have this cosine to the first here in the middle, let's take the sine squared x and change it into something that just has cosine squared x. So I'm going to bring this left side down, not make any changes here, but there is something that we can replace sine squared x with. And this is back from the original Pythagorean trig identity. Sine squared plus cosine squared equals 1. And so instead of writing sine squared x, I'm going to replace it with 1 minus cosine squared x. Again, if you just subtract cosine squared from both sides, that leaves you with 1 minus cosine squared is equal to sine squared. And now, the 1's on both sides we can subtract. Everything is in terms of cosine to a power. So now then, let's do like we all do for all equations. Bring this negative cosine squared x to the left. So let's add it. And so we'll have 2 cosine squared x minus cosine of x is equal to 0. Well, we have two terms here that have a common factor. That common factor is cosine of x to the first power. So I'm going to factor the cosine of x out. Then that will leave for this first term 2 cosine of x. For the last term, minus 1 equals 0. Now we have two linear factors. That's what we want. Factors to the first power. So I'm going to take both of them and set them equal to 0. Cosine of x equals 0, just like we had in the previous problem, example 1. And then here we have 2 cosine of x minus 1 is equal to 0. So let's solve the first one. Now again, what we're looking at over here, we're between 0 and 2 pi. We're between 0 and 2 pi now. Where is cosine of some angle equal to 0? Now again, since the restriction is given in radians, I'm going to give the value for x also in terms of radians. The previous one was in degrees, but now x is equal to either pi over 2, or that's pi over 2 going up, but then if you continue, pi is -1, 3 pi over 2 is another value where cosine of 3 pi over 2 is 0. Okay? And so that's it the first time around for this first factor. Cosine of x equals 0 gives two solutions, x equals pi over 2 or 3 pi over 2. Let's take the second factor. Let's add 1 to both sides. So 2 cosine of x is equal to 1, and then divide both sides by 2. Cosine of x is equal to 1/2. Again, where does this occur the first time through one complete revolution on the circle? Let's see, cosine of x equals 1/2. Where is that? The first time is at pi over 3. That's positive. And so all the irreducible multiples of pi over 3 are going to have a 1/2. It's just, is it positive or negative? Well, 2 pi over 3, second quadrant, that's going to be negative. 3 pi over 3, that reduces 4 pi over 3. That's in the third quadrant. Cosine is also negative there. We're looking for positive. So we go on to 5 pi over 3. And this is the second case where this cosine of x would equal 1/2, fourth quadrant. So we have 4 solutions. We have x is equal to pi over 2, 3 pi over 2, pi over 3, or 5 pi over 3. Those are the ones that work. Now, let's take a look at example 3. Its directions. Solve this equation for all real values. All of them. We're not restricting to principal values. We're not restricting just to the first time around the circle. We want to hit all of them. So let's take this equation, 2 secant squared x minus tangent to the fourth x equals -1. And again, let's take a look at what we can do to change it into something that's a little bit nicer. Well, again, I don't want to be working with a secant and a tangent at the same time. That's like having 2 different variables. But again, from one of our original 3 Pythagorean trig identities, there's something that relates secant squared with tangent squared. And that is secant squared is 1 plus tangent squared of x. I'm plugging that in right there. Minus tangent to the fourth is equal to -1. Now then, all we have on both sides are tangents and their powers. We don't have multiple trigonometric functions here. Well, let's go through and distribute the 2. This will be 2 plus 2 tan squared x minus tangent to the fourth x plus 1 equals 0. Bringing everything to one side for a second. Probably could have left it over there, but I want to go through and take a look at this. The 2 up front with the 1 back here. I'm going to rewrite this minus tangent to the fourth x plus 2 tan squared x plus 3 equals 0. This is exactly what's there. The thing that we don't like is our leading term is negative. That's our highest, but we don't want our highest power to be negative. We don't care about all the others. They can be. So let's multiply both sides through by -1. When we do this, we're going to have tan to the fourth minus 2 tan squared x minus 3 is equal to 0. Now, here's one of the cases where we have a form. This is in a quadratic form. And so I'm going to make a u substitution here. I'm going to let u equal tangent squared x. Now, replacing tangent squared in this tangent to the fourth, that's going to be u squared minus 2u minus 3 equals 0. Well, now this is a very simple quadratic equation to factor. So let's write down the factorization here. U minus 3 times u plus 1, setting both factors equal to 0. And then solving, we have u equals 3, or u is equal to -1. Once we've solved for u, our variable that we substituted, let's undo that substitution and say tangent squared x equals 3, or tangent squared x equals -1. Well, tangent squared of x is equal to 3. That means if we take the square root of both sides here, we'll have tangent of x is equal to plus or minus root 3. Now, where do we have a root 3? You may need to go back into sine and cosine values. Sine of pi over 3 is root 3 over 2. Cosine is 1/2. So when x is equal to pi over 3, we have a positive root 3. But it's not just for pi over 3. It's for all multiples of pi over 3. This is the positive case. So I'm going to take pi over 3 plus, well, where's the next time that occurs? Well, it's directly pi radians, or 180 degrees away from this. So I'm going to put plus pi in, all right? And that gets half of them. That's the positive case. We also have x is equal to negative pi over 3, all right? Negative pi over 3. Now, if we wanted to, we could go around and take that as a 5 pi over 3, but we can do it this way as well. And so these are all of our values when we have tangent of x is equal to plus or minus the square root of 3. This will get every one of those places forever. Now, what about this second one, tangent squared x equals -1? Well, remember, this is shorthand for something squared equals -1, and that's tangent that's being squared. We can't square anything and get a negative number. This doesn't make any sense, so we have to throw this out. It's not going to give us any real solutions, and so what we're left with are these right here. Those are our solutions for example 3. All right. Let's take a look at example 5, our last one that we'll do from this set. It says solve 2 sine of theta plus 1 is greater than 0, and again it says a particular interval from theta between 0, including 0, up to 2 pi, not including the 2 pi. So here's our theta. And again, it's the first time around the circle, but we're not going all the way to where we start repeating again. Well, this is no longer an equation, it's now an inequality. Well, we still have to treat it the same. Sine of theta, 2 sine of theta, is greater than -1. We'll do that one first. and then divide both sides by 2 and get sine of theta is greater than negative 1/2. Now let's think about this for a second. We've got a particular value of sine that's going to give us a negative 1/2. Where's the first time that it gives us a positive 1/2? Because again, if we're in the first quadrant, we get the absolute value. We can find out where these others are. Again, since I'm in radians for my restrictions over here, I'm going to give my answer also in radian measure. Well, sine of theta, that's pi over 6. Sine of pi over 6 is 1/2. Well, the next irreducible multiple of pi over 6, pi over 2 pi over 6, that reduces 3 pi over 6, that reduces 4 pi over 6, that reduces 5 pi over 6. Let me put the equals here. 5 pi over 6 is where we actually hit negative 1/2. We've got to have that value first, where it's actually equal to. Then we keep going. Well, 6 pi over 6 reduces, and then 7 pi over 6, that's the next irreducible multiple of pi over 6. Well, we got to keep going. These are both our negatives here, where it's equal to, and so we're not going to be able to include either one of these, but these are our endpoints. When we get over to 11 pi over 6, then we're over in the fourth quadrant, and so we'll use those there. All right, let me get this one here. 11 pi over 6. Now, I spoke wrong. 5 pi over 6, that's still positive 1/2. I can't use that one. I'm taking it off. These are my two that actually check out, the 7 pi over 6 and the 11 pi over 6. Now, it says that the value is greater than 1/2 for wherever we are. Let me move this up just a little bit. So I'm just going to put a circle on here. And let's just see where this takes us. Again, looking at the unit circle. Well, our value says that theta has got to be greater than, sine of theta has got to be greater than negative 1/2. Well, if we're anywhere in the first two quadrants, right there, anywhere on the circle, sine is positive everywhere up there, except at the endpoints. So that's greater than negative 1/2 for sure. And then, as we're coming down until we get to 7 pi over 6, putting an open circle right there, right? Well, any value on this, you give me any value, any radian measure there for theta, and that's going to be bigger than negative 1/2. But as soon as you get to 7 pi over 6, that's equal to negative 1/2. And all of the values on this side in the green, we can't use because they're going to be less than. Down here at 3 pi over 2, it's negative 1. That's not greater than negative 1/2. But as soon as we get to 11 pi over 6, all of a sudden, that's equal to negative 1/2. Okay? Well, again, it doesn't have the or equal to, it's just greater than only. But as soon as I move beyond it, these are now going to be greater than negative 1/2. They're still negative values, but now they are bigger than. So how do we solve? What's our solution? Because remember, our restrictions at the beginning, theta is between 0 and 2 pi. Well, let's take a look at that. We're going to say theta is any value bigger than or equal to 0, less than 7 pi over 6. All right, that's one part. That's the first part going around from over here at the x-axis until you get to 7 pi over 6. And then the second part is going to be when you get to the 11 pi over 6. So we'll say, or you could be between 11 pi over 6 for theta. Again, not equal to, because that's not greater than or equal to, and less than 2 pi. Why is it less than, not less than, or equal to? Again, the original restriction was 0, greater than or equal to 0, less than 2 pi. And that's what we have here for our solutions. All right? The assignment for this is on RenWeb, so make sure that you understand these types of problems. These are what we have in this section, and we'll see how we do on it.